Hey everybody. Let me just consult my notes here. Oops. Oh jeez. I looked something up right before it started and now everything's bonkers. Okay. Hello. Today we're going to be talking about something really neat. Root functions. They're called radicals. Radicals. But a radical is a square root function. There are other root functions. Cube root, quart root. Let's focus on the square root for this one. So the deal is, root functions are inverse functions. So we're going to be talking, so a lot of the work that we've done, we're going to see some other broader inverse functions in the future, but right now, root functions are one that you're actually fairly familiar with operationally. So we're going to talk about how understanding them as, how understanding a root function, a radical function, as an inverse actually helps us understand aspects, properties of the function. This isn't the only time we're going to hear this particular song, but this is probably the first time you'll hear about it applied to a function that you already know something about, the root function. Okay? By the end of it, you'll be able to identify why the root is not the inverse of the square. We'll talk more about that later. And you'll be able to recognize the features of the parabola in the shape of the root function, and you'll be able to sketch a root function, and you'll be able to recognize the domain and range of a radical function. Okay? It sounds very complicated, but it's actually fairly specific, easy to understand. So what we're going to do is we're going to start with this graph. I've graphed a parabola, y is equal to x squared. And we're going to try to draw the inverse function corresponding to this. Okay. Now we've talked a lot about how to graph the inverse of an expression. We do it with red pen, I guess. So you cut. Notice that I've scaled the x and y axis. This is so that I have some more points that I can see on this graph. So this one here is. Let me label them all. A, B, C, D, E, F, and a point up here is G. So this point here is -3, 9. This point here is -2, 4. This point here is -1, 1. Here is 0, 0. Here is 1, 1. And you go 2, 4. And this one here is 3, 9. Okay? We're going to draw the mirror image of this line through the xy axis. We're essentially going to draw its mirror image. Okay, so let's start with A. You switch the x and y terms. So point A prime is going to be at 9 minus 3. So 9 minus 3 is over here. This is where A prime is. It's at 9 minus 3. I've just inverted these two coordinates. The next one is at 4 minus 2. So 4 is here, minus 2 is here. So that's B prime. 4 minus 2. The next one's 1 minus 1. There. So that's C prime is at 1 minus 1. D prime is at 0, 0. E prime is at 1, 1. F prime is going to be at 4, 2. So here's F prime. 4, 2. And G prime, this guy's mirror image is going to be 9, 3. G prime is at 9, 3. And then I want to reflect the shape here, but essentially that's going to go. Oh, I'm so bad at drawing these. You know what? Let's try to draw it better here. So this blue line here that I've just drawn, this is the reflection of the original function in the xy line, right? So this should represent its inverse. Is the blue line a function? The answer is no. Why not? It doesn't pass the vertical line test. So for any, hey, x is equal to 9. There's two outputs. One of the outputs is 3, and the other output is minus 3. Okay? So there's two outputs, so it doesn't satisfy the vertical line test. So what do we do? Well, before I go on, we know that, look, it's a function. Y is equal to x squared. What's the inverse of this? It's supposed to be the square root, right? So like 3 squared is equal to 9, and if I take the square root of 9, you should go back 3. Isn't the square root the inverse of x squared? Aren't these two inverse functions? The short answer is kind of. Kind of. The way it goes is this. We know that this particular line, it doesn't satisfy the vertical line test. So this function here, it's not one-to-one. It's not invertible. But it's still really handy to essentially have an operation that gives me the inverse number. So how do I take this line that's this shape and turn it into something with an inverse that is invertible? And the answer is we restrict its domain. So what we do is we say, okay, instead of this particular fun function, we're going to only consider this function half of this function, okay? So they say, okay, well, let's forget about these points here. Yeah? Doing so cancels out this reflection, these points down here. And the result is this blue line here it is a function. It passes the vertical line test. Okay? So what we did is we ignored half of this original function. Oh geez. We ignored half of the original function, only considered the half that's either on one side or the other side of the vertex, and the result is this line here. And this line here is the square root of the function y is equal to square root of x. This is the inverse of this operation in the sense that it's the inverse of this operation if I'm only considering positive inputs. So I'm only taking half the parabola. The square root is thus a function only because we've taken half of the parabola, okay? And this is, we've talked about testing to see if something's an inverse, and there's a sweet proof that shows that these two aren't proper inverses of each other, okay? So f of x is equal to x squared, g of x is equal to square root of x. We talked about how to test this particular example last time. So f of x, wait, hold on, boop, sorry. F of 3, you stick the number 3 in there. What do you get? 9. You stick 9 in the square root function, and you get back 3. If you try this for a negative number, minus 4 all squared is plus 16. Stick plus 16 in the square root function, and you get back plus 4. So this number and this number aren't the same. Okay. The square root only operates as an inverse when x is positive. For all the other numbers, for inputs where x is negative, it's not properly the inverse function. You don't get the same number out. A lot of the, well, hold on. This is generally part of the theory. This is part of the reason. Being able to explain things this way is the reason we spent an hour doing those other videos. Essentially, there's an important lesson here about how can we tell if something's a root. So what we've done is we say that this function, when x is positive, and this function are inverses of one another. Okay. With that in mind, I want to address a few other fun things here. The first thing is it has to do with the shape of the square root function. Because the shape of the square root function, or any root function rather, it's shaped kind of like this. Okay? And the reason it's shaped like that is actually pretty cool. It's shaped like a tipped over parabola. It's shaped like a parabola tipped sideways. So this is the reflection of this. It's shaped like a parabola tipped sideways, where I've only drawn half of the U. And that means that a lot of the different aspects of the parabola show up as features in the shape of the root function. So, like, the chief distinguishing feature of the parabola is that what's it called? Vertex. The highest point or the lowest point, the bottom of the U, right? The vertex of a parabola corresponds to the leftmost point of the square root function. You know what? I'm going to just take a second here, and I'm going to get rid of some of the details on this graph, and I'm going to draw in my parabola again and draw its complete thing so you can see a little bit more of what I'm talking about. Okay. So what I'm trying to say here is parabolas have vertexes. They always go down to a lowest point or a highest point. When I reflect the shape of the parabola through this orange line, this x equals y line, to get the inverse, you end up with a u tipped over. Right? And so the location where the parabola can't get any lower, in this case, so it can't get any lower than this, corresponds to the root function having a limit. It can't go any left more than this point because of the shape of the parabola. Okay? So that's what I'm trying to get at. The vertex, oops, hold on. The vertex in the parabola corresponds to this right-hand endpoint, this endpoint in the root function. Let me write that down. Just so you know how important I think this is. The root function, they're called radicals, has a sideways parabola shape. where we've chosen either the top or the bottom of the sideways parabola shape. Okay, and the vertex of the parabola corresponds to the end of the root function. So, in other words, the vertex is right here. That means that when I take my root function based on this, it's going to have an endpoint like that. Where's my blue one? Or it's going to meet a cusp. Okay? And so root functions are generally shaped like, they'll be shaped like that, kind of, or they'll be shaped like this, the bottom half of the parabola, or they could be mirroring different parabolas. You can get a shape like that, or a shape like this. Now, before I go on, I want to make a note here. I want to connect this to a point that we were talking about before. When we, okay, here, just give me a second. Yeah, and then there. All right. When we're, as a procedure, like when we're completing the square, we use the square root function, right? So as part of the completing the square thing, you'll have a term like x plus 3 squared is equal to 25, and then you'll take the square root of both sides, and then x plus 3 is equal to plus or minus square root 25. How does this plus or minus come into it? Like, why do we do this plus or minus deal? And the answer here is that your parabolas always have an upper and a lower branch when we tip the parabola sideways. When you look at the mirror image of the original parabola, the inverse operation, it always has two branches. And so in this case, the plus and the minus correspond to the top branch, positive, and the bottom branch, negative. Okay? So that's why we do it. It's because operationally, in terms of functions, the square root function is only one of the two. It's only, by default, it's only the top part. And so you have to reintroduce a minus sign in here to acknowledge that there is also a bottom branch. Okay? All right, so without further ado, I want to just go back to this, emphasizing that there's a relationship between the shape of the parabola and the shape of the root function. Okay, so different. Every radical. Okay, so before we go on radical expressions, what's a radical expression? The basic radical expressions that we'll expect you to talk about will look something like this. Plus square root, maybe plus 2 square root 5 minus x. Or maybe it'll look like 3 minus 4 times square root x plus 2. Or maybe it will look like this. 7 plus square root x minus 3. Something like that, okay? Radical expressions, in this case, the kinds I'm going to ask you to be able to draw, they always have some constant number, and then plus or minus another constant. And then on the inside, it will always be a monomial, x plus some number or x minus some number, something like that, okay? It will never be a quadratic inside there. So the deal here is that each and every radical you can draw is actually part of the inverse of a parabola. I want to emphasize the connection between the algebra that I've taught you to do and graphing the thing to understand what's going on, just because it's pretty fun. So let's start with let's try an example rather. X minus 3 all squared plus 2. what does this graph look like? You already know how to draw the vertex of these things. So oops. Okay, so the vertex is at 3, 2. 1, 2, 3, 1, 2. This is where the vertex of the thing is, and it's pointing up. One, two, three, four. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 9. So this is what our quadratic function looks like as a parabola. I'm making a point. Okay, so I didn't sketch the graph. I graphed the graph here. I'm not usually going to ask you to graph, especially on the test. It's kind of a waste of time checking each of these points. It's more helpful. It's sufficient usually in terms of testing to just do the way I taught you. Find the vertex pointing up or pointing down. Maybe find one or two other points. Here I wanted to graph it just because we're going to be drawing its inverse. Okay? So now let's sketch the inverse of this dude. Okay. So this point here is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, I think it's supposed to be up here. Oops. One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Got to be as precise as you can when you're doing demos. All right. There you go. So that's the graph y is equal to x minus 3 all squared plus 2. Let's draw its inverse. Okay. So first off, I need to recognize where all these points are. This is at 0, 11. This is at 1, 2, 3, 4, 5, 6, 6. This is at 2, 3. This is at 3, 2. This is at 4, 3. This one here is at 5, 6. And this one here is at 6, 11. Alright, so now we just need to figure out where the mirror images of these points are. You know what? I could have done it the other way, where I just kind of count them out. Maybe I'll do that. That's more fun. Oops. Yeah, these graph-heavy episodes have a lot of me poking around. So this one is 11 points up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So it's going to be 11 points to the right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. X. This point is 1, 2, 3, 4, 5. So it's going to be 1, 2, 3, 4, 5. X. This one is 1 up, so it's going to be 1 like that. This one's the one to the side, so it's going to be 1 up. This one is 1 to the right, so it's going to be like that. This one is 1 above, so it's going to be 1 to the right. And this one's 1, 2, 3, 4, 5, so it's going to be 1, 2, 3, 4, 5 to the right. All right, so that's what the mirror image looks like. Okay. Let's see what I get when I try to invert this function. We've already had enough experience doing this. You just go -2 on both sides. I take the square root of both sides. I move that 3 over. And then I switch the x and the y. I probably should have done this first. Okay. So, what we see here, oh geez, they're both green. What we see here is not one but two root functions. One of them is y is equal to 3 plus x minus 2, and the other is y is equal to 3 minus x minus 2. So let's just think about what we know about square roots. Okay? The thing inside a square root can only be positive, or if you plug it into your calculator, you're going to get the word error. Okay? So that has to be positive. X minus 2 is only positive when x is bigger than 2. And as we see, these lines we have sketched are only defined when x is a number that's bigger than 2. Okay? Also, so when x is a number smaller than 2, neither of these gives me any, the calculator says error for both of them. Okay? So, the next thing to note here is that this one, when x is equal to 2, that's as small as this term gets. So when x is equal to 2, this term in the expression is 0, and y is equal to 3. 3. So you see the vertex point here, the mirror of the vertex, is at x equals 2, y is equal to 3. Just like we expect. The vertex of this thing is at x is equal to 3, y is equal to 2. And the vertex of the sideways parabola is at x equals 2, y is equal to 3. Just like we might expect. So, as I was saying, the thing in the square root can only be positive, and that means that this term here, even with the square root, this term is only going to get bigger, right? So in this expression, in the top one, that's going to be a function that increases. It gets higher the bigger x is. Gets higher the bigger x is. This second, ooh, that's weird. The second expression, it's 3 minus this thing is only going to get bigger. Oops. So this expression's only going to get smaller and smaller and smaller, and more negative. It's that branch. Okay. So when you turn the expression sideways, when you graph the parabola and then flip the parabola sideways, what we get is two expressions, one on top of the other. This one here is y is equal to 3 plus x minus 2, and this one here is y is equal to 3 minus x minus 2. Okay? So the fact that there's two branches and how they fit together, if I were to graph them, it makes a little bit of sense. Also, you can note that each of these is a reflection of a different part of the parabola. Okay? Let me kind of clear some room here. This part here is the left-hand side of the parabola. Yeah? The top part here is the reflection of this part of the parabola. Does that make sense? So the long and the short of it is, we can't express this sideways parabola with a single square root function. So instead, we express it with two, both starting and ending at the same point. Okay, so one of the aspects of what we're talking about is essentially I want you to get a sense of how the shape of the parabola, which I assume you actually know pretty well by now, is it's a mirror image of the shape of the root function with this addition that we're only going to plot half of it. I'm going to teach you how to do sketch your root function without having to even talk about what the parabola shape is, but I do want this connection to be in your head a little bit. Okay. So I want to do one practice with you. Y is equal to minus 1/2 x minus 2 all squared plus 3. What does this graph look like? X, Y. All right, let's talk about the inverse of this. So if you do a little bit of algebra, you see 2 minus 6 minus 2x. If you do a little bit of algebra to figure out what the inverse of this expression is, you get, there's a plus or minus. Let's focus on this one, okay? So suppose somebody asks you to sketch a graph of this function. You know that this function and your original one are related, okay? Because I just did the algebra. You can try the algebra yourself too. I'm going to erase it just so you know that these two expressions are related. How do you sketch this graph? How do you sketch the graph of this one here? Well, one way to do it would be to just blankly sketch this graph and then figure out which side of this graph corresponds to this line. Okay? What do I mean by that? Well, this one has a vertex at 2 and 3. So 1, 2, 1, 2, 3. Right there's the vertex. You know what, maybe I'll blow this up a little bit more. Oh no. Ah. Oh, gross. Alright, start a new one. Okay. 1, 2, there's the x-axis. 1, 2, 3, there's the y-axis. So the vertex is going to be right there. When x is equal to 0, that's equal to minus 2, minus 1, so the y-intercept will be there. And then its mirror image point will be here. And so this is what our graph looks like. Parabola, fine. Okay. So I want to one way to sketch this function, because I know that it comes from this one, is to start by sketching this one. Okay, and now the question is, which of these two sides is it reflecting? Is it reflecting this side, or is it reflecting this side? Right? Remember, each of these branches corresponds to one side or the other of the parabola. So the question here is, which side is this one reflecting? Is there any way to tell that? Sure there is. Sure there is. We can look at this expression inside here, right? So like I said, the thing about the roots is that, wait, hold on. That's going down, and so it's probably that one. So let's start with the vertex. It's 2 above, so it's going to be 2 over here. So the vertex of our graph is going to be like there. Okay. Is it when x is equal to how do you tell? Sorry, my notes don't tell me how I figured out that this was the right side of it. Well, the other side of it, there's going to be 2 sides of this. 2 plus 6 minus 2x. And one of them is going to be increasing. The other is going to be decreasing. I think it's the one that's decreasing is the one to the left of the parabola. Yeah. So what you do is you say, okay, if it's negative, then it's going to be that side. And if it was positive, then it's going to be that side. The one we want is negative, so it's just going to be this region here. So let's forget about this side of the parabola. And then we can mirror image these points to figure out what the graph of this expression looks like. So this one is 2 to the right, and that means it's going to be 2 down. So the graph is going to look like that. Y is equal to 2 minus square root 6 minus 2x. Yeah. Fun, huh? Okay. So that's why rational functions, or sorry, radical functions are shaped the way they are. They're just essentially a reflection of one half or the other half of a parabola. And so the shape of them is going to reflect that. There's going to be like, where this part, on our parabola comes up, it's steep, and then it flattens out and is shallow. What you're going to do is you're going to have, its mirror image is going to be shallow and then goes up and is super steep at the last part. Okay? They're both going to, or this one's going to truncate on the x-axis. It's going to be defined rather because the parabola is defined for a whole bunch of values that are, in this case, less than some value of y. Its inverse here, its reflected image, is going to be defined for a whole bunch of terms that are less than some value in terms of x. So like we said before with the domains and ranges of these expressions switching, because we're mirroring half a parabola, it'll have a domain that's half of the x line. It'll be all the values of x that are lower than some number, and that's going to turn into the range of this being all the values of y below or above some number. And similarly, because our parabolas have a maximum or minimum point, the inputs, the domains of our parabolas are going to be less than some number. So that's the reason. That said, graphing things like this is like a huge waste of time. There's a way easier way to do that, and that's to just get a sense of how rationals work. And I'd like you to do it because, you know, composite functions and domains and ranges all come into it. Okay? So, without further ado, let's talk about how to graph a rational. Sketching radical functions. Okay. So, the basic shape of your radical expression is going to fall into one of 4 different basic shapes. Because it's the mirror image, mirror reflection of some parabola or another, it can be shaped like this. It can be shaped like this. It can be shaped like this. Or it can be shaped like this. That's a horrible drawing. Shaped like that. Where each of these are, you know, half of a reflected parabola. Okay? So there's 2 aspects pretty much that we need to figure out. Well, 3. If somebody gives me a radical expression, I have to interpret the numbers in here to get 3 pieces of information. First, you want to figure out where the endpoint is, where on the xy axis it's located. The second thing you need to figure out is whether it's increasing, this it gets higher, or decreasing, gets lower. Whether it lies above the endpoint or below the endpoint. Vertically, I mean. And the third thing you want to figure out is whether it's going to the left, like these ones are, or whether it's going to the right. Like, wait, no, that's, these ones are going to the right, these ones are going to the left. Okay? So there's 4 things, essentially, pieces of information that you need to get. Well, 3. Okay, so what are they? Where's the endpoint? Two, find the domain. Are we going to the left or right? 3, find the range. These 3 pieces of information are going to tell you what, essentially, all the information you need to be able to draw a sketch of a root function. All you need is a sketch. Okay, so which is it going to be? First, let's talk about the root. Figure out the endpoint. And point. All of the behavior of this weird expression comes from the square root function. Okay? The square root function has a few just basic behaviors. One of them is that it doesn't allow negative inputs. you take out your calculator and you go square root of -2, and it will say error. Okay? In other words, x needs to be bigger than or equal to 0. So that's one basic aspect of the square root function. And another is it's always increasing. So square root of x is always going to be bigger than or equal to 0. You can see these attributes when we sketched it at the very start. In fact, I can probably scroll up. It's a pretty nice graph. I'm pretty proud of it. Yeah, see? You'll note that this function, it starts here. So it's not defined for any x less than 0. And it's always, except for this one place where it's 0, it's always above the x-axis. Okay? Because it's that part of the parabola. So operationally, the square root function, just this basic square root function, hold on. We're thinking about this as like a weird composite function, FYI. So it's made of polynomial operation, square root operation. Okay. So a lot of the behavior of the shape of the graph inherits the behavior, these specific behaviors of the basic square root function, shaped like that. Okay. So the location of this endpoint is where the input of the root function is equal to 0. So we have to ask ourselves, what value of x in the function we're given, what value of x makes this thing equal to 0? It's x equals 2. Okay. And then you plug that in, and when x is equal to 2, y is equal to -3 plus square root of 0, so it's equal to -3. And so the endpoint is at 2 minus 3. So if I wanted to graph it, oops. Okay. 1, 2, 3, 4. -1, -2, -3. So I know that the endpoint of my graph is going to be right there at 2 minus 3. And the only thing I have to figure out now is whether the function goes like that, whether it goes like that, whether it goes like that, or whether it goes like that out of that point. So step 1 is finding the endpoint. Step 2 is finding the domain. The reason there's a domain, usually in most continuous functions like polynomials, the domain is going to be any number you want. Any number. You put it into x squared, whatever. In this case, though, the domain has to be a number where what we enter into the square root operation is a positive number. So what you do is you take the thing inside the square root and you ask yourself, where is this positive? And that's something I've taught you how to do. You know it's positive when x is bigger than 2. Great. So the domain is x bigger than 2. And what that tells you is, on our graph is only going to be defined for values of x bigger than 2, which rules out these bottom ones to the left. So one of these two has to be the graph. Next step, I need to talk about the range. That's where all the stuff outside the square root function comes up. Okay? What was it? -3 plus square root x minus 2. I've already been trying to teach you how to think about the different terms and the behavior of the different terms. We're going to repeat that process here. We essentially say, okay, this thing. That thing's always going to be positive. Generally speaking, there's some numbers outside of it. In this case, it's the number 1. Fine, whatever. How does this affect the outputs? Well, because this term, the square root term, is positive for any value of x, it means that the output of this is always going to be bigger than minus 3. Because as this term increases, it's going to get bigger than minus 3, and it's going to get more and more positive. So it's pointing upwards. So can't be that shape. It has to be this shape. The shorthand is, if there's a positive number in front, it's shaped like this. And if it's a negative number, it's shaped like that. Okay? So the domain here is x bigger than 2, and the range is y bigger than minus 3. So let's try a couple of these ourselves. Like I said, once we understand the relationship between these and parabolas, it becomes clear that all these radical expressions will all have the same shape. They'll all be shaped like these kind of chunks of sideways u's. And once you know that, you can just start reading off the behavior from the function itself. So let's try yourself. Try it. Y is equal to 3 minus 2, 4 minus x. All right. There's 3 steps. One of them is figuring out the vertex, the endpoint, and the others are figuring out which way it goes from there. So you figure out the endpoint by looking at the stuff under the square root function, setting that to equal 0, because it can't be negative, right? So 0 is like the border between good and bad. So it's going to be, its endpoint's going to be at 4. And when x is equal to 4, y is equal to 3. How about minus 2 square root 4 minus 4, which is equal to 3 minus 2 square root 0, which is equal to 3 minus 0, which is equal to 3. So it's equal to 3. Oh, come on. Be nice. All right. So 1, 2, 3, 4. 1, 2, 3. So then the question is, does it go like that, or like that, or like that, or like that? And to figure those out, I need to figure out information about the domain. It's the domain. When is 4 minus x bigger than 0? Move the x to the side. It's bigger when x is less than 4. So x is equal to 4 is right there. So x less than 4 is this region here. Right? So that means that these two are out. It's got to be the top or the bottom remaining. Okay. 3. The range. Y is equal to 3 minus 2, 4 minus x. This term here is always positive, right? And a positive number times a negative number is a negative number. And so as this thing gets bigger and bigger, y is going to get more and more negative. Hold on. When I say bigger and bigger, it's not quite clear. When x gets farther and farther away from 4, it's going to get more and more negative. Alternatively, you can just look at that minus sign and say, oh, it's this one down here. And then you can sketch the graph. It doesn't have to be a good graph. All I want you to be able to do is draw this line. And then you're like, well, what about the x-intercept? Don't worry about the x-intercept. What about the y-intercept? Don't worry about that. Don't even worry about that. Don't focus on that. All I want you to do is figure out where the endpoint is, the domain, and the range, and then do a little doodle like that. Okay? That's it. Let's try another one. y is equal to minus 2 plus square root 2 plus x. Why don't you pause the video and give this one a try? Where is the, oh geez, where is the endpoint? Which shape does it have? All right, so 2 plus x is equal to 0. 1. Its endpoint at x is equal to minus 2. And see, minus 2, these two cancel, right? And then y is equal to minus 2. So its endpoint is minus 2, minus 2. Its endpoint is right here. So then the question is, does it go like this, or like this, or like this, or like this? 2, domain. We want to be positive. So it's got to be bigger than minus 2. X equals minus 2 is here, so it's defined when x is any bigger number than that on the right. So that means that it has to be this one or this one. Range. This term's positive, and so it's always going to be bigger than minus 2. Which means that this one's out, and that's the shape. Okay? And maybe I should draw it in red pen. And this is the shape. Okay, so that's all I need you to do. That's plenty of skills. Let's review them all. Okay, so quadratic. Oh god, that's terrible. That's still pretty bad. Quadratic functions, y is equal to x squared plus 3x minus 7, whatever. These are parabolas. Okay? They have a max or min value of y. If I turn it sideways, I get something that isn't a function, but with some modifications, it's related to the square root, which is the inverse of half a parabola. In other words, we had to be really careful when we define these because quadratics don't generally have inverses. But the concept of an inverse and how to graph it really informed us about why the square root behaves the way it does. Specifically, it let us qualify this whole, what's the shape of it? How does it have to do with parabolas? The min-max value of y corresponds to min-max, minimum or maximum input on that graph. Okay? And so both of these have domains and ranges. Which qualify what the shape of the thing looks like. Okay? So the domains and the ranges of our quadratic that are cut in half inform what the domain and range of the square root are. And vice versa, I guess, if you want. Okay. Well, that's it for this particular video. In terms of understanding, in terms of raw calculations that I expect you to do, it's just that last one where I'm like, here's a quadratic, sketch its like this one where I'm like, here's a simple radical function. I want you to sketch what it looks like. Understanding why the sketch looks the way it does And why we're allowed to take the shortcuts we do all comes down to understanding inverse functions and all those other things we talked about. So that's it for today. I'll talk to you later.